In this video, I'll be giving a brief introduction to semiconductor physics, and I'll be approaching it a bit differently. So instead of, deep diving into the technical details of the subject, what I would rather do is focus on one of the key goals of studying this subject. And in that way, the learning will become more meaningful. And of course, it'll even be exciting. So that way we will get a clearer perspective of why we are studying this subject. Right, so let's get started. We are given a block of semiconductor, and the objective is to find how the current changes through the semiconductor as I apply a varying voltage across it, right? So in other words, what I'm trying to tell is I have to find what is the function that maps this voltage to current. So this is what we are trying to find. So there are two ways of doing this, and the first method is what is called as finding the mathematical model. And what this means is just doing empirical data fit. For example, using some simple techniques such as linear regression or some complex nonlinear data fitting techniques, right? You use this to find this model. And I'll just show an example of simple linear regression. First thing is we have to gather the data points. So first thing is we need data points. And how do we get the data points? We do this experiment multiple number of times, right? So basically you apply a voltage V1 and you measure current I1, and that is one set of data point. So that is V1, I1. Next you again repeat the same experiment and you apply a voltage V2 and you will see what is the current. That will be I2. You do this n number of times until you get n number of data points, and that n can be any big number. For example, let's say we have done 10,000 such experiments. So once you do this experiment, what you do, you plot all these points on a graph. There's your voltage and there's your current. Your graph will look something like this. Okay, so this is an example of a simple linear regression. So the graph looks something like this. Now what we do is we try to choose a random model based on the equation. Like we know what the equation of this model should look like. So it should look like y is equal to mx plus c. We just don't know what is m and what is c. These are the unknown for us. So we'll just assume some random value, and so let our model be this one, right? So this is the actual measured data, and this is the model prediction. So this is what model prediction. So now what we do at each data point, we see what is the predicted value from our model and what is the actual measured data, and we find the difference between these 2 points, right? So this actually gives the error from the actual measured data to the model that we have used, and the goal is we have to try to minimize this error. So in many cases what we usually do is we try to reduce the sum of the squared errors, or in some cases root mean squared error, right? We try to reduce this. That depends on your model or your fitting technique that you're using. So there are various minimization technique that you can use to reduce this error. So what you will be doing is you will have a loop. You keep repeating this process. So after one iteration, probably you will end up with a graph like this, right? This is your second iteration, and again what you do is you find at data point what is the error, and this error again you try to reduce, and it's an iterative process. And after few iterations, finally you will end up with the measured data. Whatever measured data you had and whatever the model is predicting, it will almost be same, or there might be a bit error. Okay, so this is one way of doing it. What this will give y is equal to the current m v plus c. This is what it gives. And as you can see, right, this model doesn't actually give any physical insight about the device. Like it doesn't tell what parameters of the device you have to optimize in order to improve your current or reduce your current based on the applications, right? So this is just a mathematical model. It doesn't have any physical meaning as such, right? So this is one way of doing it. So the second way of doing it is what we call as the theoretical model. This model is actually arrived from your basic laws of physics, such as your conservation laws, your Maxwell equations, your Newton's equations, and your quantum mechanics. So using these equations, we've tried to find what is the function that maps this voltage to the current. So let's get started with a simple equation of current that we know. So we know that current is nothing but rate of change of charge, that is dq by dt. This charge q, the total charge, is given by q n into v. So I'll explain what each of this term is. Q is the charge of each carrier. So in semiconductors, we often use this term called carriers because the flow of current is not just because of electrons, right? You have something called as holes that also contribute to the flow of current. So we generally use the term called carrier, and the charge of each carrier is actually given by 1.6 into 10 power minus 19 coulomb. That is actually the charge of your electron. So N is your carrier concentration. So it is given in terms of per cubic centimeter. V is your volume. So this carrier concentration is not a simple expression in semiconductors, So if you have metal, it is very easy to find what is N, because for a given piece of metal, N is nothing but your total number of valence electrons into the total number of atoms present in that block. So the block that you had, right? So it's easy to find the carrier concentration in metals because almost all your valence electrons take part in your current conduction. But whereas in semiconductors, it is not a simple expression to find this carrier concentration. So what we do is we find something called as density of states, and we multiply it with a Fermi function, and we integrate this expression for a given range of energies. This results in the carrier concentration. And this density of states and Fermi function is actually arrived from quantum mechanics and statistical mechanics. So I won't go in much detail about this. I'll just stop here. I'll make a separate video where I actually explain each of these topics in more detail. So this is how we arrive at the carrier concentration. Next thing is we have to find what is the volume. So we have this block of semiconductor. So let's assume the current is flowing in this direction. So the volume is given by this area of cross section multiplied by this distance, right? So what is this distance? Say we know the velocity at which these carriers are moving from this point to this point. It is Vd, and they take time t, and this distance is just given by Vd into t. So even in the case of semiconductors, this Vd is not a simple thing to find. So if you had these electrons, say in a vacuum, and you apply a voltage V, so the velocity at which these electrons travel in a vacuum is quite different from what they do in semiconductors. So it is not a simple thing to find. So we actually have we have various models for this. So one is what we call the drift, the other is called diffusion, and one more is called ballistic, where your transistors are very small and now you have to consider the quantum effect. This is how you arrive at the velocity of the electrons. Now finally plugging all those things into the equation of charge, we get charge is equal to Qn A Vd into T. So finding the rate of change of charge, which is nothing but the current, we get Q N A to Vd. So this is the final expression of the current. I mean, so even if the final expression looks like it doesn't have any voltage dependence, but it turns out that when you find your carrier concentration and your velocity, it actually depends on your applied voltage. Okay. So this is what we call the physical model of current, or the theoretical model. So we can clearly see that this equation gives a lot of physical significance. So it tells on what physical parameters the current depends on. So we know what we have to tweak in order to improve the performance of the device. So I mean, improve the performance such as increase the current, or else in some cases you'll have to reduce the current. If it is a leakage current, you'll have to reduce it, right? So this will tell, actually, if you have this model, right, it will actually tell what parameters you have to tweak in order to reduce this leakage current. So this is the way how we find the theoretical model of the current versus voltage in a semiconductor. So that's the end of this video. So we just saw how a simple current equation actually comes from various aspects of semiconductor physics, right? So what I plan to do is, in future I'll probably try to explain each of these topics separately. And finally, these devices will be used to build circuits. So, right, we have to understand how to design circuits using usable circuits using these devices. So I'll probably even make short videos on the design of circuits such as amplifiers and so on. And that's it for this video, and see you in the next one.